graph analysis. It's important to understand the behavior of graphs. So some key points that we should make sure we understand is that we know the relationship between the derivatives and integrals. So here I've given you going to the right, we're differentiating, going to the left, we're integrating. So if we start at f of x, our f of x, we want to go to the right, and the slope of f of x is going to be determined by the f prime, and the slope of f prime will give us the second derivative, which also relates all the way back to the original function in terms of concavity. And the reverse is also true, but going to from right to left, we are integrating. And if we start with the f prime double prime graph, the area under the f double prime graph represents the displacement on the f prime, and the area under the f prime represents displacement on the original f function. So it's important to keep track of the units and the context of the problems. A good one would be, a good example of that is when we talk about position, velocity, acceleration. So derivative of position is velocity, derivative of velocity is acceleration. And if we anti-differentiate acceleration, we get velocity, or the area underneath acceleration is a change in velocity. Area under velocity is a change in position or displacement. So it's good to kind of relate the functions to their shapes. So if we talk about, first of all, the second derivative here. If we talk about a positive second derivative, we're talking about concave up on the original function f. If we talk about a negative second derivative, we're talking about a concave down on the original f graph. We should also be aware how the second derivative affects the derivative function and vice versa. If we have a positive second derivative, that means that the change of the first derivative is positive, so we have this sloping up situation. And so if we have sloping up, that also means that it must be concave up on the original function. So those things are all interrelated, and the reverse can be true of our sloping down. So if we have a negative second derivative, that means that the first derivative is sloping down, which means that the f of x must be concave down. And so the reverse is also true. If it's concave down, the first derivative must be sloping down, and then the second derivative must be a negative y coordinate. And then there's this relationship between the derivative and the original function. A positive first derivative means sloping up. A negative first derivative means sloping down original function f. We can also relate these to the shapes of the graph. So if we take a look at the shape of f prime, we can predict the behavior in f of x. So if we take a look at a graph that cuts through the x-axis in this way, now it's cutting from left to right down. That means that the f prime is positive on one side, and it means it's negative on the other side. Well, the behavior in f of x means that, well, that point here, where it goes through 0, is going to be a vertex. And it's going to be like this because it is sloping up. So that positive means it's sloping up. And the negative on down here means it's sloping down. Okay, so we're going to end up with this max point. So when it cuts through the x-axis like that, we're talking about a maximum point. If we have a 0 here, that also means a horizontal tangent. Okay, that's going to represent a horizontal tangent. On the right side of that, the f prime value is positive. That means it must be sloping up. On the left side of that, the y values are negative, so the f prime values are negative. That means the behavior in f must be sloping down. So we must end up with this min point like this. So when it cuts through the x-axis, the f prime cuts through the x-axis in this way, we end up with this shape of graph. Now, we can also talk about how it changes direction in f prime. If something changes direction in f prime, that means that we're going from a positive slope in f prime. Well, a positive slope in f prime means that it is a positive second derivative. Okay, so that means we're going from a concave up situation. We have a concave up situation here. So sloping up means concave up. When we change direction at that point, what's going to happen at that coordinate? Okay, so we're going from sloping up, which is concave up, and then on the other side of that, now we're going to be sloping down. Okay, sloping down means that the slope of the slope is negative. That means the second derivative is negative. That means we have a concave down situation. Okay, so anytime we change direction of slope on the derivative function, we are indicating that we have an inflection point. So in this case, we have inflection, okay, a change in direction on the slope graph. When it cuts through the x-axis from left to right going up, we have a min. When we cut across through the x-axis left to right going down, that must be a max. Okay, and we can analyze that based on the slopes. So in example 1, we've been given just some polynomial function. We want increasing, decreasing regions. We want concave up, concave down. So to do this, I'm going to make a slope chart and a concavity chart based on my second derivative and my first derivative. Let me just color code this here. So my first derivative is in red, and my second derivative will do in blue. So f double prime x and f prime of x. So our first derivative, we're going to differentiate. We end up with 900 x squared minus 5. Okay, we're gonna make that equal to 0. So we end up with making this equal to 0. We're gonna end up with, in this case, 5 over 900 is equal to x squared. So my x is going to be equal to square root 5 over square root of 900, which is 30. So we get plus minus root 5 over 30. So I have a negative root 5 over 30 point here. There's a 0 slope here. A positive root 5 over 30. There's a 0 slope here. And I can just check these slopes with my derivative function. So I'm going to test my derivative, f prime at 0. If I plug in 0, I get negative. I know that's negative slope through here. We've got a positive slope there. And then checking some other coordinates, f prime, well, let's just choose x equals 1. Okay, that's going to be bigger than root 5 over 30. At x equal 1 is positive. F prime at negative 1. Again, we're going to end up with positive 1. Positive. So we have positive slope here and positive slope here. So we can see based on the graph that we have a max and min at max at negative root 5 over 30, a min at root 5 over 30. And we can see our increasing and decreasing regions. Okay, we can set this as, write this as inequalities as well. For the concavity, we want the second derivative. So working out the second derivative, we're going to end up with 1,800 x. Okay, and in this case here, we're going to make this equal to 0. That's going to give us x is 0. So at x is 0, we have a 0 concavity. We can test our concavities to the left and right. So f double prime of negative is going to give us negative. So we know that we have negative concavity here, and we can see that based on our slope chart, that's also true. And then f double prime of any positive number is going to give us positive concavity. And again, from our slope chart, we can see that that's also true. They are consistent with that. And because we have a change in concavity, we can see that there is an inflection point at x equals 0.